Got it? Automotive electronics test 2. According to Ohm's law, what's the resistance when 1 volt pushes 1 amp of current through a conductor? You remember Ohm's law?
Is it 1?
No, I don't.
Yeah, it's not hard to remember.
Is it 1 ohm?
Yes, exactly. 1 volt pushes. You remember that because you saw that thing the other day. You may need to show him that file and let him go through it. 1 volt pushes 1 amp through 1 ohm. 1 volt pushes 1 amp through 1 ohm. Say that with me. 1 volt pushes 1 amp through 1 ohm, right? Volt is push. The amp is what's flowing. Ohm's resistance. Got it? Not too complicated. Technician A says the total amperage in a parallel circuit equals the sum of individual branch circuits. Technician B says the amperage in a series circuit is the same anywhere in the circuit. C is right. Both of those guys are right. Here's a series circuit. Watch this. See this? Just so we'll all be on the same sheet. All right. Let's say that I put this many light bulbs in series. All right. Just hook it up. All of those, each one of those is going to get, depending on the resistance of the bulb, each one of them is going to get, if they're all the same, each one's going to get a third, right? You're going to drop a third of it at each place until all of it's gone. So basically, if you measure the current in this circuit, it's going to be the same anywhere you measure it. Any circuit is like that, if you measure the current anywhere in it. Now the caveat is, let's do a series parallel circuit. All right, what if we had a bulb there, like we did here, and then out here, we had a bunch of little bulbs. And each one of them had its own ground. Got it? That's a parallel circuit. This is a series circuit. It's got to go through everything on a series circuit. Each bulb's got its own ground. If you lose one bulb, the rest of these still burn. If you lose this bulb, everything goes dark. Hear me? So you break anything in a series circuit, the rest of the whole circuit goes down. But if you break just one in a parallel, it's not that way. So that's the difference between series and parallel. You understand what I mean? Think about series being a 1-lane dirt road and parallel being a 4-lane highway. If somebody breaks down on a 1-lane dirt road, everything stops, right? Nobody can get past him. But on a parallel circuit, you got multiple paths. You can actually go around whoever it is that is standing there with their hood up. What's the sum of the voltage drops in a series circuit equal to? A, the amperage, B, the resistance, C, the source voltage, or D, the shunt circuit voltage. Now you remember what I told you here? Every one of these is going to be dropping some until it's all gone. So the total drop is going to be equal to whatever's there. And this is what I mean by that. I got a battery, minus, and I've got right here. Let's just do this. Let's go ahead and put, well, I'm going to go ahead and loop this around. Now in here, I'm going to put a resistor. And then right here, I don't know why I can't draw a resistor better than that. I'm going to put a bulb. And right here, I'm going to put a switch, and that switch is closed. If I take my meter and measure right here, I'm going to read how much voltage is being lost at that resistor, right? Take another meter, and I put it right here. I measured how much voltage is lost at that light. And if the switch has got dirty contacts, I'm going to read voltage drop right there with my meter. Each one of these voltage drops, if you add them all up, is going to equal whatever the battery voltage is. They may not all be even, but whatever you find, you're going to have, all of those are going to equal what that is. You're going to drop it all. So that means you're not going to read any voltage on the negative side at all. But right here you're going to read 12. Right here you might read 8. Right there you might read 6. Right there you're going to read nothing. Hear me? Everybody got it? All right. You remember that from that little thing you went through the other day? All right. So the formula for Ohm's law is E equal volts, 1 I equal amperes, and R equals resistance. E equals I times R. Is that right? R equals E times 1. This is something here. See? Watch this. E, I, R. All right, you remember that? Can you explain it? Which one of these is right?
All of them.
Okay, so what you're saying is if I multiply that times that, no. You're going to multiply this times this to get that, right?
Yeah.
You're going to divide that one by that one to get this one, and divide that one by that one to get that one. So, if this is 12, and this is 4, and that's 3. See that? If that's 4, that's going to be 3. If that's 3, that's going to be 4. This right here is the one that these other two are working with. All right, so that's how Ohm's law works. You see, that's pretty smooth. So what's the correct formula there? It would be B. E equals I times R. That's what B is. All right. Huh?
What was 3?
3 was
So what was 2 and 3?
the source voltage. The source voltage being the battery, all the voltage drops are going to be equal to the source voltage. What will be adding resistance to a series circuit? Excuse me. What will adding resistance to a series circuit cause? Less current to flow. Anytime you add resistance to any circuit, it causes less current to flow, right? That's what Ohm's law is all about. Got me? All right. Voltage drop is what? We talked about it a minute ago. Voltage used up when pushing current through resistance. If I measure on both sides of a battery cable, like if I measure at the positive terminal and the positive hookup on the battery, spin the starter, I'm going to find out how much is being lost. This is what happens when somebody says, I put a starter on my car, it still starts slow. I put a battery on my car, it still starts slow. I don't know why, run, 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 run. So you say, okay, what we want to do is we're going to see if we're dropping voltage on the ground side, which would be from the negative battery terminal to the body of the starter. We're going to go from the positive battery terminal to the big post on the starter, and we're going to spin it. Each time we're checking those, you're allowed to have 1/10 of 1 volt on the negative side and a 1/2 volt on the positive side. That's all you're allowed to have. In a series circuit, which of the following statements is correct? The circuit amperage will increase as more resistance is added. That's not true. The total resistance is the sum of all resistances in the circuit. Is that true? That's a series circuit. That's true, isn't it? That is true, is it not? Number 7. The total resistance is the sum of all resistances in a circuit. Remember the series circuit. All right, I got a resistor, I got a resistor, I got a resistor, 10, 10, 10. Measure here with my ohm meter. How much am I going to get?
30.
30. Bingo. Now, parallel is a little trickier than that. If you got a parallel, and we'll talk about that on another question here in a minute, I'm sure. I got 3 resistors. They're all wired together, and they're 10, 10, 10. And I'm going to measure right here. What have I got? 3.3. It's going to be cut in 3, right? It's going to be, each one's giving you another pass for current flow, so it reduces the resistance every time, you got me? All right, that's how that works. Let's see, in a series circuit, in all the following statements about voltage drops are true except what? Voltage drop can be measured with a voltmeter. Is that true? What have I been talking about up here, guys? Y'all asleep? Need some coffee? What's up? Can you measure voltage drop with a voltmeter? Yes or no? Yes. Quincy? Talk loud. All right, we need to be able to hear you. All right. Because you've measured voltage drop before, haven't you? You've done it. What'd you use?
Voltmeter.
What was that?
Voltmeter.
What was that you say again?
Voltmeter.
Voltmeter. You used a voltmeter to do that. Okay. Okay, what's another one? Voltage drop is a conversion of electrical energy from another form of energy. That's true, isn't it? All of the voltage from the source must be dropped before it returns to the source. That's what we were just talking about, isn't it? As so you measure the total voltage drops, you're going to get the source voltage. And so corrosion is a contributor to voltage drop. So D is the one that is the accept answer. You can't say corrosion is not a contributor to voltage drop. If you got resistance, you've also got heat. That's why resistors are made out of ceramic. So be aware of that too. You know, things get hot when you get resistance. What's the amperage flowing through a 36 watt bulb in a 12 volt circuit?
B.
What did you say?
B.
B is good. Very good. Listen to her. And how did you get that?
Divide 12 and 36.
See, look at that, sharp as tack. All right, let's look at here. Technician A says when a magnetic field is moved across the conductor, voltage will be induced in the conductor. Technician B says when a conductor is moved across a magnetic field, voltage will be induced in the conductor. Both those guys are right. I could take a loop of copper wire. I could hook a meter to it, and I could take a magnet and just pass it through that wire, and that voltage, we'd be making voltage. That's how those little sensors work. You remember guys seeing a scope pattern we were looking at the other day? That's the same reason we got that, same way we got that. Okay, technician A says an atom that loses or gains one electron is balanced. Technician B says an atom that loses or gains one electron is called a charged particle or ion. That's B only. It is a charged particle or ion. You know how far it is from the center of an atom to the first electron ring? If you brought it up to the size of a pin. If you brought the center of the atom, of the nucleus of an atom, up to the size of the head of a pin, how close would the first electron ring be to that nucleus? 300 yards. Atoms are mostly empty space. Got it? The proportional ratio of solid material to empty space in an atom is like the difference between 1 second and 30 million years. Isn't that amazing? Atoms are mostly empty space and we're all made out of atoms. That means we're mostly empty space, right? Doesn't feel like it when you step on the scale, does it? Not to me anyway. All right. Let's see. The current wait a minute. Technician A says testing with a voltmeter can determine the voltage drop across the headlights. Technician B says a voltmeter can determine excessive resistance in the circuit. Both of those guys are right. Okay, how are we going to test that? You know where your headlight plugs in? You know, we got 3 wires going to our headlight, right? We got our headlight bulb right here. Okay, we got 2 headlight bulbs actually. And each headlight bulb, this is the way we're going to draw this, has got 2 filaments in it, right? Okay. And we're just, it's going to be slightly different. You're going to have to look at it and make sure. But I got 2 filaments like this. This one here is grounded. This one here and that one there are basically going to your multifunction switch. Okay, let's say that I had this headlight and this headlight. See, that's actually going there, that's going there, that's going there, there through the connector. This headlight here was dim and that one was bright. And I want to know why. Well, when I click it to dim, I'm going to be firing up this wire. This wire's not going to be hot. This one is, right? Okay, how does that power get there? It starts from the battery, it goes through the headlight switch, it leaves the headlight switch, it goes through the multifunction switch, which is the one you brighten dim, and then it comes out here. Unless it's done with relays, and a lot of them are nowadays. But the point is, we want to know why this light's dim. Now, first thing I'm going to do is I'm going to go to my battery, right here, where a battery terminal is, and I'm going to turn on my headlights, and I'm going to take my meter, right here, and I'm going to hook it between that positive battery terminal. I'll touch it to the center of the post if I can. And then I'm going to take the other one and I'm going to go right here to the dim headlight. If the bright and dim headlights, maybe if this headlight's not burning as bright as that one and it's supposed to, what I read right here is going to tell me if I'm losing voltage in between here and there. It won't tell me where I'm losing it. It will just tell me I'm losing it. And then you got to walk back through the circuit to, zero in on it. It can be in a connector that's got salt corrosion in it. It can be a burned up switch. It can be all kinds of stuff. A wire that got too hot, a cold splice joint, whatever. What if you measured and there's not any voltage drop there that amounts to anything? That's when you're going to go to the negative side of the battery. And you're going to go from there to this ground right here. And you're going to see if you're dropping voltage on the ground. You got it? Everybody understand what I'm talking about here? Get a voltmeter. And it's easy to do because the headlights are right there, typically. I mean, some of them, on some of these darn Mazdas and everything, they're buying the fender shield. But if you get to it, and you can actually go right there, and you can find out why that headlight's dim. And you'll know how to track that down. And everybody needs to know how to do that. Would you like to do that? All right, then. That's what I was talking about. So that's how you do that. Okay, so let's move on here. We got some stuff to go here. Let's see, in a closed circuit with a capacitor, when will current stop flowing? A. What do you think? No, that's B actually. When the voltage across the capacitor plates becomes equal to the source voltage. What is a capacitor? Here's a capacitor, right here. That's a capacitor. It basically, you notice it's got a minus on one side of it, Brian. This has got a Quincy. It's got, it says minus on one side, and the other side doesn't need to be marked with plus because there's only two sides to it. It is polarity sensitive, but if you put power and ground in there, as soon as this thing comes to a full charge, and it's just, this is, think of a capacitor as just a very short life battery. And I can hook a battery up to this thing right here, and I can charge it up to 12 volts, and then I can take one of these little LEDs and touch it from one side to the other. The LEDs are polarity sensitive too, and it'll, like that. Or I can hook this up, to 12 volts, and then I can disconnect it and connect it to my scope. You remember the other day when I was doing that? It'll actually spike up to 12 volts and then taper off. But it bleeds off real easy. Now this right here is made to take ripples out of circuits and all that kind of thing, but that's a capacitor. There's all different sizes and shapes, but that's a capacitor right there. The condenser in a distributor that's got points and condenser is a capacitor. And it'll actually hold up to 30, 40,000 volts, if you actually lay it on the engine block and jump to that little wire. Okay, I can show you that later. Don't ever take a condenser out of a distributor if somebody tries to hand you one, because it's probably charged up and they want to shock you. You know what I mean? Your dad may know about that. All right. Now then, let's see. The display of a digital voltmeter is indicating 236 millivolts. Which of the following is the same as this value? 0.236, 0.2, that's millivolt, 0.236 volts, 23.6 volts, or 0.000236 volts. Which one of those is right?
A.
Okay, now, wait a minute. Okay, how many millivolts is 1 volt? 1,000. Don't play dumb with me. All right, look. That's 1,000 millivolts is 1 volt. Okay, so if you write 0.236 volts, that's 236 of these units, isn't it? That makes sense? Got it?
Yeah.
You got it? You got it. You got it, huh?
Yeah.
It's similar to thousandths of an inch, only you're measuring thousandths of a volt. You've got to know how to write that stuff. If I give you a question and you answer it wrong, shame on you, because I've already explained it to you really well. Here's something else you need to do. Remember I told you, explain it to somebody else that will listen, and you'll get to where you know it better. Burn this in. You hear me? All right then. That's it. Remember, 1.000 is a volt. All right, so here we go. Let me see. Technician A says amperage is the same at any point in a series circuit. That's true. Technician B says the total resistance is the sum of all resistances. Yeah, we're hammering on that one, but that's true too. And that's, so C is going to be that one. Technician A says conventional theory of current flow states current flows from positive to negative. That is true. Technician B says current flows randomly. A is the only one right about that. Electronic theory says current flows from negative to positive because electrons are negatively charged. Conventional theory, which ignores the fact that electrons are negatively charged, says that current flows from positive to negative. And in our testing, what do we do first if we got something that doesn't work? We check the doggone fuse. Is that on the negative side or the positive side? Positive side, right? So you're checking from positive to negative when you're tracking the problem. A lot of people don't think about the dark side. You remember what Darth Vader said? You don't know the power of the dark side. The dark side of the circuit is the ground side. But there's current flow in that too, right? All right, he's laughing about that. Got a chuckle out of Quincy. That never happens. All right, let me see here. Let me see. Let's see. 3 10-ohm resistors are wired in parallel. What's the total resistance? What? Nope. You guys weren't paying attention, were you? What did I draw on the board a while ago?
3.3.
3.3. There you go. A tail light bulb is glowing dimly. A voltmeter placed across the bulb reads 4 volts. Technician A says there may be excessive resistance in the ground circuit. Technician B says there may be excessive resistance in the power feed circuit. Who's correct about that?
B.
What do you think? Could be either one. See here? This is what we're talking about. We got a bulb, and it's grounded. Let's just make it real simple. And we measure from here to here while it's burning, with our meter, and we read 4 volts. Our source voltage, now, this is not a complete question, because they should say the source voltage is 12 volts, but we're only reading 4. Could we have resistance here and have that, and cause it to only have 4 volts? Yes, we could. If we did a voltage drop test between here and ground, how many volts would we read if the ground was the problem? What's 12 minus 4?
8.
We'd have an 8-volt voltage drop. But we could have partial voltage drop on both sides. If we went from the positive to the positive on the, battery, we may read a voltage drop too. But the point is, if there's only 4 volts making it to the bulb, you're dropping some somewhere. That's why your starter spins slow when you got a bad battery cable or a bad connection or a bad ground or something. I could tell you some stories. Of course, you all know that now, can't you? All right. Technician A says voltage will not exist between any 2 points in a circuit if the potential is 0. Technician B says corrosion is not a contributing factor to voltage drop. Who's right? A is the only one that's right, and technician A says power is found by multiplying voltage times current. Technician B says power is expressed as wattage. Who's correct about that? Both those guys are right. You multiply voltage times amps, which is current, you're going to get your watts.
What was
18?
18?
Wait a minute, I dropped the paper. 18 was C.
What was
2. What are we going back up there for? That was C. Were you half asleep when we did that one? All right. I hope you guys picked up something you can take with you on this here.